Hello, everyone. Hope everyone's doing well. I don't think I've seen you guys since last Friday. It's been too long. So hopefully you were able to view Tuesday's lesson where I was absent. And if you don't, it's still available. So you just, whatever the date was, I think it was the 16th. So find AP1 216. That lesson was purely qualitative, so there was no quiz for that because the math involved is quite a bit more complicated. You know, it's more like college level math to incorporate friction and driving force and all that stuff. So today we are going to talk about simple harmonic motion graphs. Okay. So basically all the graphs that you would need to know how to make regarding simple harmonic motion. Now, it's going to be useful to recall some of those formulas that we learned last time. So, or not last time, but a couple of times ago. So in particular, we learned the following equations. We have the period of a mass spring system, which was 2 pi square root of m over k. All right. We have that the max speed is square root of k over m times the amplitude. We have that the maximum acceleration is k over m times the amplitude. And I'm trying to think. We have that the total amount of energy can be thought of as 1/2 k a squared. So this is the total energy evaluated at the extreme points where the velocity is 0. Or we could evaluate the extreme point as the mass is passing through equilibrium, in which case we have 1/2 m v max squared. Okay, so these are the equations we're going to use today. So let's start off with a position time graph of simple harmonic motion. So we have position and time. And so I'm going to draw just one complete period of simple harmonic motion. So it looks kind of like this. Okay, so that is going to be 1 period. All right, so that is a full period. So what we want to do, the first thing we want to do is we want to go ahead and graph the velocity as a function of time. Now I find it helpful to draw it directly below so that we can get the times to line up. So for example, here is 1 period. Okay, so now what we're going to do is we're going to pick 5 points, and the points are where the graph crosses the time axis, and then the peaks and the valleys. Okay, and so what we're going to do is to go from position to velocity. If you recall from motion graphs, to go from position to velocity, you get the slope. Okay, so we're going to take these 5 points and we're going to evaluate the slope. Okay, so if I look right here, look at this point, the slope is positive. That's sloped up. Okay, so that means that the value of the velocity at this location is positive. Okay. Oh, by the way, I forgot to add that the position graph wiggles between plus an amplitude and minus an amplitude. Okay. So we take the slope. At this point, the slope is positive. Here, at this point, we can see that, you know, if you want to know what the slope is going to look like, you can kind of imagine that you're a skier. So imagine that you're a skier, and the slope is basically the direction that your skis would be pointing. Okay? So if you're sitting on the top of a mountain, your skis are going to be pointed flat. So that's a slope of 0. So at that time, I have a slope of 0. Here, imagine you're a skier. There's your skis, and you can see that it's sloped downward at that point, so that is a negative slope. Okay. And then here, if you were right here, your skis would be horizontal, so that's a 0 slope at that time. Okay, and here the slope is positive. So all I'm doing is I'm taking these 5 points and I'm just seeing, is the slope positive, negative, or 0? Okay, and so what I can see is I have 5 points, and so now what I'm going to do, now that I have 5 points, is I'm just going to connect the graph with a trig function. Okay, so this looks like cosine to me, so I'll just kind of smoothly connect it like that. And so that is going to be the shape of the velocity time graph. Okay, but it's not enough to simply know the shape. What we also have to know is what are the values that the velocity graph wiggles between. Okay, because all the trig functions, they wiggle between a maximum value and a minimum value. Okay, so to do that, I notice that I have an equation for the maximum velocity. It's right here. Okay, the maximum velocity is square root of k over m times the amplitude. So that means that this, and here, right here, is the maximum value of the velocity. So this must be square root of k over m times a. Okay? And then if it goes up to positive square root of k over m times a, it's going to go down to negative square root of k over m times a. All right? So when we're making simple harmonic motion graphs, what you want to do is you want to pick some points and get the sign of the slope. Is it positive, negative, or 0? So you have a couple of dots on the graph. You connect the dots with a nice smooth curve, and then you use the formula to find the values that the graph is going to wiggle between. Okay, so that's the procedure. So now we can go even one further. So we can go to the acceleration as a function of time. Okay. And again, here is a full period. So now what we're going to do is I'm going to choose the same 5 points. Now to get the acceleration, that is the slope of the velocity graph. So now I have to take these 5 points and identify their slopes. So right here I can see that the velocity is, or that the slope is 0. So at the corresponding time, I'm going to mark the acceleration as 0. All right. Here, I can see that the slope is negative. That's a negative slope. So down here on the acceleration graph, I'm going to mark a negative value because it's a negative slope. Here, I can see that the slope is 0. So I'm going to mark at that particular time that the slope is 0. Here, I can see that the slope is positive. So I will mark at that time a positive value for the slope. And then here I can see that, again, the graph is flat, so the slope is 0 at that time. Okay? So I have my 5 points. And now what I do is I just connect them with a smooth curve. Like that. All right, so that is the shape of the acceleration versus time graph. And then once we have the general shape, what we need to do is we need to figure out what values does the acceleration wiggle between. Okay, and so to do that, I can see that the maximum acceleration is k over m times the amplitude. So that means that this graph must go between plus k over m times a and minus k over m times a. So I found the extreme values of that graph. Okay? So that is how you get position, velocity, and acceleration versus time graphs. But that's not all we can make. So we're going to make actually 3 more graphs here. One graph we could do, and I will draw that one next to this, is gonna see. So this is about this wide. I want to make this accurate. So there's a full period. All right, and here's time. So this is a graph versus time, and we're going to graph the elastic potential energy versus time. So why did I draw that graph next to this graph? Well, it's because the formula for elastic potential energy is 1/2 kx squared. All right. So the key idea here is that we take our position graph and we square it to get the elastic potential energy. All right. And so when you square a negative number, it becomes positive. When you square 0, it's still 0. When you square a positive number, it's still positive. So we're going to take these same 5 points and we're just going to square them and see what the sign is, okay? So right here I have 0 because the position is 0 there. 0 squared is 0. So I will mark 0 at that time. A positive number squared here is a positive number. 0 here, 0 squared is 0. I have a negative number squared, which is going to be positive. So I will mark positive that time. And then here I have 0 squared, which is 0. So now I have 5 points, and I can connect them with a smooth curve. Like that. So that is your potential energy versus time. One of the things I want to point out is that the position graph has one peak and one valley, just one peak in a period, okay? But the potential energy graph has 2 peaks in a period, so it wiggles twice as fast. Now, why is that? It's because your potential energy is maximized when you're at position plus A or when you're at position minus A. All right? So just keep that in mind. So the smallest value that the potential energy can take is 0. And then the biggest value, so what is the biggest value? Well, I know that the energy is 1/2 Ka squared. So the biggest value that this can take is 1/2 Ka squared. All right. So that is how we get the potential energy as a function of time. Keep in mind, what was I going to say? That's fine. So now you might guess we are going to graph the kinetic energy as a function of time. All right. Now the formula for kinetic energy, all right, is 1/2 mv squared. So that is why I am drawing the kinetic energy graph next to the velocity graph, because I'm going to square the velocity graph. So I want to have it nearby, so because I'm going to use this graph as the basis for that graph. Okay. So we have to square the velocity graph. So I'm going to go to these 5 points, and I'm going to use the fact that 0 squared is 0, a positive number squared is a positive number, a negative number squared is a positive number. So here I have a positive number squared, and I'm going to square it, which is still a positive number. Here I have 0 squared, which is 0. Here I have a negative number squared, which is positive. Here I have 0 squared, which is 0. And here I have a positive number squared, which is positive. All right, so it kind of looks like a W. So now I connect the dots with a smooth curve. So a lot of times for this one, people are tempted to um, draw something that looks like this. They kind of will draw. All right. So this has cusps. These are called cusps. But the actual graph does not have cusps. See how it rounds out at the bottom. It doesn't have a point at the bottom. Okay, so our general strategy is to make the general shape of the graph by looking at these 5 points in a single period. Okay, and then figuring out what does it wiggle between using the formulas up here. So what I can see is that the kinetic energy is going to go between 0 and 1/2 mv max squared, because that is the maximum value of the kinetic energy. I should point out that really we could use 1/2 Ka squared as the maximum if we wanted to. Okay. Why? That's because, your maximum elastic potential energy is the same value as your maximum kinetic energy. Okay. Or here we could use 1/2 mv max squared. All right. So the final graph that we are going to make is a graph of the total energy versus time. Total energy. So the total energy is kinetic plus potential. Okay, and we can figure out what this graph should look like in a number of different ways. One way is we could say, well, it's simple harmonic motion, so I know that energy is conserved. And if something is conserved, then it's not changing as time goes on. So the graph just looks flat. Okay? That's supposed to be flat. This doesn't look like a very flat line to me, but maybe like this. Another way we could see that it is going to be a flat graph is by noticing that when the potential energy is high, at that same moment, the kinetic energy is low. When the potential energy is low, the kinetic energy is high at that same moment. So what you can see is that when one goes up, the other one goes down, so that they always add to a constant. All right? What is the value of that constant? Well, the value is just going to be the total amount of energy. So it's just 1/2 Ka squared. All right? I did want to, so if you're not in calculus, don't worry about it, but I did want to connect this to calculus, okay? So what we can see here is this position. So I'm gonna have just a really brief discussion of calculus, and then we're gonna do an example with numbers, okay? So what we can see here is that this is a graph of sine, right? Because it starts at 0 and then it rises to a peak. So this is a graph of sine. So if x is going like sine, then to get the velocity, we have to take the derivative, and the derivative of sine is cosine. Okay? And we can see that this graph looks like a cosine graph. It starts out at a high value and it drops. Okay? Similarly, so to go from position to velocity, you take the derivative. To go from velocity to acceleration, you take the derivative again. The derivative of cosine is minus sine. Okay? And you can see that this is indeed the shape of the minus sine graph. So that's nice. then we can see to get the potential energy, I have to square the position. So the potential energy graph is going to look like sine squared. Okay? And in fact, if you plug sine squared in the calculator, it looks exactly like this. Okay? The kinetic energy graph, we have to square the velocity. So the kinetic energy graph kind of looks like velocity squared, so it's going to be a cosine squared. All right? And so indeed, that is the shape of the cosine squared graph. And then kind of where it all comes together is when we say that the total energy is K plus U, kinetic plus potential, which is going to be like sine squared plus cosine squared. And you probably know from your math class that sine squared plus cosine squared equals 1, which is a constant. So that is how it works. So this is a sine squared graph plus a cosine squared graph are going to equal a constant graph. So I think that's kind of neat just to kind of pull in calculus and the math of trig functions. All right, so let's do a specific example. So for this example, let's suppose we have a 3 kilogram mass. So you are told that this is a 3 kilogram mass, and you are given its position as a function of time. Okay? So in this graph, on the previous page, I was just talking conceptually about graphs, the shape of the graph. So notice how I didn't put position in meters and time in seconds, because I'm just talking conceptually about it. But now we're talking concretely about the motion. So now I'm going to put units in. All right? So I have position in meters, and I have time in seconds. And I'm going to draw my position time graph. Okay? And so we'll say that that is 0.4 seconds. We will say that this is the amplitude. Okay, so the amplitude is going to be, let's say, 0.5 meters. And so then this would be minus 0.5. So from this graph, we are able to determine two things. We know that the amplitude, okay, is 0.5 meters. And we know that the period, so a full back and forth, is 0.4 seconds. Okay? Another thing you want to notice is that this graph is representing negative cosine. So your position graph isn't always going to be sine. It could be it could be cosine, it could be negative cosine, it could be negative sine. So yeah. So now what I'm going to do is I'm going to do a sidebar calculation where I figure out all of these formulas. Okay? Figure out everything I need to know from those formulas. All right? So the first thing I'm going to do is I'm going to use period is 2 pi square root of m over k. Oops. So I know that the period is 0.4 seconds. equals 2 pi square root of m. I was told that it was a 3 kilogram mass over k. So you can see I can take this and I can solve for k. I'm not going to show the algebra, but you can. And so the k value is 740 newtons per meter. Okay, so I'm going to be using that. So now I'm going to figure out what is the maximum speed. So Vmax is square root of k over m times the amplitude. Okay, so that is going to be square root of 740 divided by 3, because I just calculated that k is 740 and the mass is 3. And then the amplitude I know is 0.5. So that gives that my maximum speed is 7.9 meters per second. Now I will get my maximum acceleration, which is just k over m times amplitude. So not square root of k over m, but k over m times amplitude. 740 divided by 3 times 0.5. Which is 123 meters per second squared. And lastly, I will get the energy, which is 1/2 Ka squared. So that's going to be 1/2 times the K value is 740. And the amplitude is 0.5. So 740 divided by 8 is 92.5 joules is the energy. So these are all the pieces of information we need to assemble the graph, all the graphs. So we'll do that. So first one I'm going to do is velocity as a function of time. And so I'm drawing that directly below position as a function of time. Okay, and again I'm putting in units because I'm talking concretely about, is it concretely or concretely? I don't know. Confusing myself. So anytime you're talking concretely about a specific problem, you need to put units on the axes. If you're just talking about conceptually, you don't need to put the units on the axes. So I'm going to take my 5 points here, 1, 2, 3, 4, 5, and I'm going to look at the slope to get, okay, to get the velocity graph. So here the slope is 0. So I'm going to mark 0 at that time. Here the slope is positive. So I'm going to mark positive at that time. Here the slope is 0. So I'm going to mark 0 at that time. Here the slope is negative. So I'm going to mark negative at that time. Here the slope is 0. So I will mark 0. So I can see I have all these graphs, or all these dots. So I just connect the dots. Okay. So I've found the general shape. That's a horrible drawing, but I did the best I could. And then all that remains is to put the numbers that the velocity graph wiggles between. And I know that I found that the maximum velocity is 7.9. So this graph has to wiggle between plus 7.9 and minus 7.9. Okay. So now let's do the acceleration graph. again, I am going to draw that directly below the velocity graph, because to get the acceleration graph, I have to find the slope of the velocity graph. So I take my 5 points, and I look at the slope. Here, the slope is positive. Here, the slope is 0. Here, the slope is negative. Here, the slope is 0. And here, the slope is positive. So I have my 5 points, and then I connect them with a nice, smooth curve as best I can. And then I see what it wiggles between. It wiggles between plus A max and minus A max. And I found that the maximum acceleration is 123 meters per second squared. So it's going to go between plus 123 and minus 123. So that's how you would get your acceleration graph. Now let's go ahead and do the potential energy versus time. Time in seconds. This will be 0.4. This is potential energy in joules. Okay? So remember, the potential energy, you square the position graph. And squaring has the effect of turning negatives into positives. So here I have a negative squared, which is a positive. Here I have 0 squared, which is 0. Here I have a positive squared, which is a positive. Here I have 0 squared, which is 0. And here I have a negative squared, which is a positive. So I have my 5 points, which I then connect with a nice, smooth curve. Please notice that the potential energy graph wiggles twice as fast. Okay? So the maximum value of the potential energy is simply the total amount of energy, which we calculated was 92.5. So this goes up to 92.5 and down to 0. Okay? Do the same thing with the kinetic energy graph. Almost done here. Time in seconds. Here's 0.4. So we want to square this graph. All right. So I've got my 5 points that I have to find the squared value. 0 squared is 0. A positive number squared is a positive number. 0 squared is 0. A negative squared is positive. And then 0 squared is 0. So I have 5 points. Connect them with a smooth curve, like so. And then, again, the maximum value of the kinetic energy is simply the total amount of energy, which is 92.5 joules. All right. Another way you could have found that graph is to simply put the peaks at the same times as the valleys of the potential energy, because because the total amount of energy is constant, when one value reaches its maximum, the other one reaches its minimum. Okay. Lastly, we will do the total energy versus time, which is the easiest graph of them all. And it is just going to sit constant at 92.5 joules. Okay? So let's review. What have we done here? We have learned how to make a bunch of graphs starting with the position time graph, we have learned how to make the velocity time graph, the acceleration time graph, the potential energy versus time, the kinetic energy versus time, and the total energy versus time. So to get velocity and acceleration, you use the slope method. And then to get the energy, you have to square one of the graphs. So squaring basically means taking all the negative values and make them positive. Once we get the general shape, what we want to do is we want to use the formulas from simple harmonic motion to figure out what does the graph wiggle between. Okay? And so that's how we make simple harmonic motion graphs. So that is my lesson for today, and I will see you in the Zoom room.